So good afternoon. I am Krishna Kumar from Krishna's classroom. So we continue our talks on linear algebra from where we left last time. So we introduced linear transformations over vector spaces, and we also talked about the range space and the null space, and that is where we stopped. We called the dimension of the range space as the rank of the linear transformation, and dimension of the null space as the nullity of the linear transformation. Now this is where we stopped last time. We continue from here. So let us put down the assumptions. Let V and W be linear spaces of dimension n and m respectively. That is dimension of V equal to over the field F. Now let us start looking at or start with a linear transformation on V. So let P from V to W be a linear transformation. Then we have defined what is called range of T . W belong to W such that a null space of T as the set of all V belonging to V such that 0. That is, you have V, W, and suppose this is the 0 element, and suppose this is NT. So this whole NT gets mapped to the 0 element. That's what you call. And suppose this is RT. RT is the range of T. Okay, so the range of RT is a subspace of W and NT is a subspace of V. So these are the things that we have said last time. NT and RT. NT is a subspace of T. And RT is then we introduce the terminology that rank of T was defined as dimension of Rt and nullity of T okay. So a general T is not. Now let us explore some examples and see what goes on. Just get a feeling for this problem. So let us start with something simple. First example. So V equal to R3. Okay. So let E be defined from V to W by PE1 equal to sum one where E1 and E2 are basis for hence T is completely defined because for any x1 x2 so we have T of which is equal to x1 of TE1 by linearity and this is equal to x1 into 1 0 1 plus one. And that gives T of equal to x1 plus x2 x2 and x1 plus x2. So what is the range of T? Range of T is equal to y1, y2, y3 such that y1 equal to y3. Okay. if you explore this, so okay, let us write down what the null space is. This is equal to the set of all x1 plus x2 such that x2 equal to 0. Therefore, you see that if you look at this, this is equal to, what is the dimension of this? All x1 x2 such that or this is simply contained in, therefore the dimension of equal to 0 or the nullity of T equal to 0. What about the dimension of RT? This you can easily see that set of all y1 plus y2 plus y1 comma y2 y3 such that y1 equal to y3 and x3 y2 equal to y2 is arbitrarily x2. Okay. Therefore, y1 equal to y3 is a plane in the three-dimensional space. Okay. Right? So it's in fact so this is this particular line, this is the line in y1 equal to y3. So you get a plane containing this line. This is the line. This is in the x1 3 plane space. So this is the plane and x2 can be arbitrary or y2 can be arbitrary. Therefore, the dimension of this plane, you see that this you can write, this set you can write as the span of that's what we have. It's the span of these two vectors. This is equal to. And these two are linearly independent, therefore these two are linearly independent, therefore dimension of 2. It's a 2-dimensional subspace of R. That's the first example. Let us keep this example. Now let us take the simple case P from Rm to Rn Rn to Rn, say, consistent with what we wrote earlier. Define it doesn't matter. It's conditions. Okay. So that is the zero operator. And you see that rank of T or RT equal to zero. And therefore dimension of is equal to 0. Null space of T equal to the whole of R. Therefore dimension of so this is the Rank-Nullity result that you have. Now let us take the third example. Now this is the P2 R. So let us define now d of if we take Pt equal to P square where P is then dt d of P to P2. So one can easily see that the null space of or the range of P is equal to the span of 1 and d, and this is, which implies dimension of RT we were using D here, so let me write D here. Null space of D, you can show that this is all constants. The polynomial C C is belongs to this collection. So these are all constant polynomials. That is all constant polynomials or polynomials. Of degree 0 and 0.3. And the dimension of equal to 1, and the dimension of RD equal to 2, dimension of ND equal to 1 in this case. So we have looked at a class of polynomials. Now let us take a fourth example. T is from defined by P of lambda 1 x1 plus lambda 2 x2 plus lambda n x1. Then range of T that's quite easy to see. Okay, therefore assume that is the null space of T is 0. Therefore, dimension of equal to 0. Similarly, you take range of T. Range of T is equal to the whole of R. Now in case B, suppose equal to 0, where K is strictly less than, then range of T is spanned by Ek plus 1 En, which implies dimension of minus T. What about the null space of T? Null space of T is, in this case, all those equal to 0, therefore that is the span of dimension of is equal to K. So we have these results. Dimension of RT is minus K. Dimension of LT equal to. Okay, let us not consider any more examples, but it is suggested that you explore more examples of this kind. And in all these cases, so make a remark, in all these cases, we observe that dimension of is equal to dimension of RT plus dimension of MT where V is the domain space. This is an observation. Okay. So what we expect possibly from our explorations on examples is that a relation of this type holds. Can we prove it? Or at least let us attempt to prove it. If we can prove it, it becomes a theorem. Okay? Therefore, let us explore this. Okay? So, is this let us explore. So, if we attempt a proof of this, how do we attempt a proof of this? So, one thing that you observe is that as null space of T enlarges, the range of T shrinks. As the null space of T becomes the bare minimum, namely consisting of only the zero vector, then you see that the range of T is as large as the domain space V. Okay, so let us prove this. Let us explore this, the proof of this. So how do we explore the proof of this? The last example is somewhat a pointer, and in fact all the other examples are also. So what we do is we start with a basis for NT. So we write theorem. I am hoping this would be true, that given a T from a linear V into W the rank of T, nullity of T, so this is the result that we are expecting to be true. So let us start with the proof of this. What we do is we start with a basis unit for NT and then enhance it or enlarge it to a basis for NT. Now enlarge it into a basis for B by adjoining xk plus 1 set to now one observes that Txi equal to 0 and Txi Txi not equal to 0 for I equal to now let us observe that range of T is the span of Txn, which is equal to span of Txk plus 1 so it's a span of Txk plus 1, Txk plus 2 etc. Txn. So we know that rank of T and nullity of T therefore which is linearly independent, therefore dimension of entity is equal to K. So the problem that you have is this. You see, you have x1, see the x1 xk here, then you have xn here. These elements get mapped to the 0 element, and this is the span of txk plus 1 tx. That's it. Now the question that you ask is, what about this? Is it linearly independent? If it is linearly independent, then we know exactly what the dimension of RT is. So let us work on that. So is independent. Now you observe, that's why let us explore this. So Ck plus 1 we are asking. Zero. This is the question that we are exploring. We can prove this. So we cannot. Okay. So you see that Ck plus 1 this is equal to T of Cn xn, and this is in general an element of what? It's an element of V. So this is in general equal to and what we are assuming is that this is equal to 0. This implies Ck plus 1 xk plus 1 null space. Therefore, which implies which is equal to sum a1 x1 plus etc ak xk, because the null space is spanned by x1 x2 etc xk, where ai's are constants. So that gives a relation that a1 x1 ak xk minus equal to 0. But now what you observe is that being a basis. And hence, equal to 0. That is all the coefficients are 0. In particular, this implies this part is 0. Which implies where we started with this dxk plus 1. Independent, which implies the dimension of the range of T is, so we have two results now. This is true, this is also. Which implies that is rank n, or the dimension of we have completed the theorem. Okay, so what we observed on the examples are really true. Okay. So we look at some of the consequences, very interesting consequence for as regards to matrices. It's a very nice result that we have. So we have already seen that the row rank and the column ranks of a given m by n matrix are equal from the elementary cases, and we give a proof based on this Rank-Nullity theorem. Okay. And application. Matrix with entries in the field. Then the row rank of A equal to okay. What is the problem? So we explore the problem. It's not the proof. We understand the problem. Okay. Now these are called the row vectors and these are called the column vectors. And the row rank is the what is called the dimension of the span of the row vectors, and column rank is the dimension of the span of the column vectors. So let us write it down. The row vectors have elements in Fn plus 1, into 1, and the equal to dimension of span of you also observe that A okay. Now this is quite easy to see. If you have x1, x2, etc., xn, then you multiply, you end up with a vector y1, y2, etc., yn. Okay. So you see that, observe. Now this is an element of F, and this is of course an by element. This is so we can also observe that this A1, A2, let us so this is A1, this is A2, so these are some of the notations that we shall require for our work. So let's make some observations. So define the operator. So T is defined EA or P of X Px, this is the definition, Px belongs to M cross 1. Okay. And you can see that T is linear, of course. So range of T this is equal to this is the one, and this you can easily see that this is in fact, you see, it is x1 times this is of the form A, where A1, A2, etc. An are the column vectors. This you can see. Hence, what you have is that the range of T is, this is equal to, for therefore, this is the linear span of and what you call the dimension of this is essentially the, so this is equal to the linearly independent subcollection which spans the range, and therefore this is equal to column rank of Now let us look at the null space of T. What about the null space of T? Null space of T equal to the set of all x such that A of x that is the solution space of the equation now we already know that if the dimension of, so it is of the form, so you see the equations are of the form A11 x1 plus zero. So this is the solution space of these set of simultaneous equations that you have. So now what you see, actually some of these equations may be dependent on others in the sense that one of them may be the certain linear combination of the others, etc. They all may be independent also. So all the possibilities do exist. Okay. So we call this the row rank. Essentially, such equations can be obtained, or the number of such equations can be determined by looking at what is called the row rank of these matrices. Therefore, so let us write down. Therefore, you see that the dimension of the span of the row vectors of A called the row rank of A actually tells you what is going to be the dimension of the null space of NT. It is not equal to that. Gives information on the dimension of NT. Precisely, if row rank of A is equal to R, which tells the number of linearly independent equations that you can generate from this, which is equivalent to this, then dimension of that's the relation that you have. So this is equal to n minus now we have two equations. Rank of T is equal to this, and dimension of NT equal to n minus row rank of A. Now you know that rank of T plus equal to n. From this we have column rank of plus n minus row rank of That completes the proof. Okay. So I think this is a nice place to stop. So we continue with these linear transformations in the coming lectures, especially linear transformations defined on a vector space. That means linear transformations defined from a vector space into itself, when they are of important, what we generally call linear operators. Thank you very much.